Well, today I'll discuss the Landau's argument. Landau's argument for maximum mass of a compact star. Basically, I will be talking about both neutron star as well as white dwarf. Now, before I proceed, let me tell you that this entire discussion that we are having, even for white dwarf, even for neutron star, here we are always considering a basic assumption, and this is very important for the neutron star in particular. And the assumption is that we are considering a non-interacting. Basically, we are considering non-interacting fermions. We are not considering any interaction between them till now. Okay, fine. Now let's proceed then. Okay, so first we will consider the maximum mass. We will try to find it for neutron star. So let us consider a static homogeneous sphere of matter. Static homogeneous sphere of matter with total mass m and radius r, right? And remember, it consists of free fermions, non-interacting fermions, each of mass small m. Okay, now you see, classically the total energy ER for a particle. So classically the total energy, right? This is the total energy of a particle of radius r is what? Is basically the sum of gravitational energy plus your kinetic energy, right? So let us write it down. So E gravity plus E kinetic, and this is just simply minus G m by r plus your E kinetic term. Right, now the energy of a particle, let us try to find this value. Now the energy of a particle is given by the relativistic Fermi Momentum relation, and let me now write it in this form. You can also write it as p square c square plus m0 square c to the power 4, right? Now here what I am using is, I am using c is equal to 1 units. So basically, and also I am writing in terms of k. So this is just k square plus m square, right? Now you see, for a fluid of free fermions, the characteristic momentum is given by the Fermi momentum, kF. Okay, and so we can just put in the value k is equal to kF. And remember, this Fermi momentum, this is related to number density as well. And what is the relation? The relation is basically n is equal to g by 6 pi square into kF cube. That g is the degeneracy factor. Now for neutrons, basically g is equal to twice s plus 1, and this is equal to 2, right? From the spin degrees of freedom. Now, for simplicity, we set the total density equal to the average density of the sphere. Total density equal to average density of sphere. And so, we can write this average density as n by v, and so we have this relation 3n by 4 pi r cube. Here, this capital N stands for the number of fermions in the sphere, and so if I equate these two, then I'll get a relation for the Fermi momentum, right? And the relation is this: Kf is equal to basically 9 pi by 2g whole to the power 1 by 3 n to the power 1 by 3 divided by r. Now, let us assume that the total mass of the sphere, is just given by the sum of masses of the fermions. So, we can have total mass m is equal to n into the mass of the non-interacting fermions, right? Free fermions, small m. Now, what we are going to do, since we are going to consider the maximum mass, and in that scenario, the energy will be extremely high for the fermions. So, basically, let us consider the ultra-relativistic limit of kinetic energy of fermion, right? Then what do we have? Then we can just write E kinetic is equal to Kf, and so the total energy of the particle we can write then becomes Er is equal to, now let me write it in other page here. Okay, so total energy we can write as Er is equal to minus G n m square divided by R plus 9 pi whole divided by twice of G whole to the power 1 by 3 n to the power 1 by 3 divided by r. Now, remember this thing scales as 1 by r, and this thing also scales as 1 by r. But remember, there is a negative sign here and there is a positive sign here. Okay. Also note that this total energy depends now only on the number of fermions in the sphere, that means n, for a fixed fermion mass m. Now, for large values of n, what will happen? First term dominates. This one will dominate, okay? And for small values of n, what will happen? Basically, the second term, this one, term dominates, okay, or kinetic term dominates. Now, as a result, in principle, there are three cases to be considered. So, three cases to be considered depending on n, or total number of fermions in star. This dependence of total number of fermions, right? This is actually a very important parameter. Now gravitation we can understand, and from the cave we have seen it is also easy to understand. So let us consider the first case. The first case is ER less than 0, and so the system is unstable as the energy gets smaller and smaller so this means system is unstable as energy gets smaller and smaller for what? R, what happens to it? R decreases as R tends to 0, so that the system collapses eventually to what? Black hole, of course. Now the next scenario, which is ER greater than 0. What happens here? Now in this case the energy can be minimized by increasing the radius until the number density and correspondingly the Fermi momentum reaches the non-relativistic region of a Fermi fluid. That is, what is it? Non-relativistic region of the Fermi fluid, basically Kf is less than 1. And then what will happen? Then in this case you see E kinetic will just be proportional to Kf square divided by Mf. Okay, and this is basically proportional to R to the power minus 2, and as a result you see a stable minimum exists for finite value of R. Okay, so let's now consider the third case, which is basically ER equal to 0, and we know this. What does this mean? This means that the system is just marginally stable. Okay, now you see, as the gravitational potential dominates for large values of n, thereby giving a negative sign for total energy, stable solutions, they exist only up to a maximum number of fermions, n max, and this, which is given by the marginally stable case. Okay, so the limit of stability ER equal to 0. What does this imply? This means basically that, let me write it down, this expression. Here, so this ER equal to 0, this gives me this relation. Or let me write this properly in different, putting this n max on the left hand side, we finally get this form. Now note that here we have set this G is equal to 1 by mp square in natural units. Okay, and this mp is basically the Planck mass. Okay, and so here you see the maximum mass, which is just this n max into the mass of free fermion, is given by this relation. Fine. Now let's find the value of the corresponding radius. For that we just put the value kf is equal to m, and this defines, basically this defines the onset of the ultra relativistic limit of fermions. Fine. And this, if we put in the value of kf that we previously determined, putting value of kf, we will get from this relation. So this is the critical radius, right? So this is what we have derived as a general result. Okay, just considering the gravitational energy and the kinetic energy of the fermions. Fine. Now let us define. Landau mass ml and correspondingly Landau radius RL by these values. ml is equal to mp cube divided by m square, and RL is equal to mp divided by m square. Now you see, so far we have not fixed the fermion mass, and the expressions, these expressions apply to any fermion, right? Any fermion star, basically. This is important. Any fermion star, each consisting of fermions non-interacting of mass m. Right. Now let us consider a neutron star. So for a neutron star, basically m will be equal to the mass of the neutron, right? And you will see that the value of the Landau mass and the Landau radius will become these values. Now, it is important to note that exact numerical calculations, they give us the value of M max around say 0.7 solar masses, and also corresponding R around 9 kilometers. Now you see that the values obtained are not too far from the numerically exact ones, again consisting of free neutrons. That means when we are considering neutron stars consisting of free neutrons, right? Now, the maximum number of neutrons for the maximum mass configuration, how much is this? So, let me write it down. Is this value? So, maximum number of neutrons for maximum mass configuration. See, what's the number? 2 into 10 to the power 57. Remember in the class, we again found this same number for the neutron star. That means the number of baryons in the neutron star. But we used a different way, a different approach. We used the condition for the collapse just before forming the black hole for a neutron star. And there we obtained the same result. Okay. Now it is also important to note that here you see the Landau mass is close to the mass of our Sun, and the number of fermions in the neutron star here is the same as that in the Sun. Okay, so let me just write down the observations. So the Landau mass is close to the mass of the Sun, and the maximum number of fermions is again the same for the Sun. This observation and another, we get the same N max from two different estimates. One is Landau's argument, and another is considering collapse of neutron star just before forming black hole. This we discussed in previous class. Okay. Fine. Now we will consider the white dwarfs. So you see, this Landau's argument, it can be readily extended to white dwarfs, and we do know that white dwarf, this material, it consists of two charged components. Electrons and nuclei. Right. Now, these balance each other such that the total charge of the white dwarf balances. Basically, vanishes. Now, which balance components, which balance each other such that total charge of white dwarf is equal to vanishes, basically. Let me write it down. It vanishes. Now for each nucleus of charge Z and mass A, there are Z electrons around, right, due to charge neutrality condition. Now the number density of electrons has to be then, with Na being the number density of nuclei. Let me write it down. So each nucleus charge Z, mass number A, and since charge is Z, so this basically there are Z electrons around due to charge neutrality. Now let Na be the number density of nuclei with mass number A, right? And so the number density of electrons, it is given by Ne is equal to Z into Na, and this is just equal to the number of protons, right, in the white dwarf. Now while electrons have a higher momentum than the nuclei due to their smaller mass, so while electrons have higher momentum than nuclei, why? Due to their smaller mass, the more massive nuclei are responsible for the total mass of white dwarf. Okay. Now the mass of nuclei, you see, to a good approximation, we can write it as nucleus mass. We can write to a good approximation as A into MP, so that mass of proton, so that the total energy for each nucleon, again total energy for each nucleus, ER, it is given by minus G M MA divided by R plus Z into KFE. This is for electrons, right? This is basically KFE. KFE is the Fermi momentum of electrons. Fine. Now let's find the total mass. So the total mass of white dwarf, what is it? It's just the sum of the mass of nuclei or by the sum of masses of the nucleons, right? So we have M is equal to Nn into Mp, or this is equal to Nn divided by A into Ma. Okay, where the total number of nucleons, this Na, let me write it down, this Nn is basically the total number of nucleons in star. Now it is important to note that the number of protons balancing the charge of electrons is basically how much? It is given by Np is equal to Z by A into Nn, right? And this is equal to Ne. So, with these modifications, let me write down the total energy for each nucleus. So, total energy for each nucleus is basically given by this relation. You see, these two terms, where we have replaced the Fermi momentum of the electrons over here in terms of the number of electrons, Ne, with G being the degeneracy factor of the electrons. Right. Now, if we write this term in terms of the number of nucleons, then we have, so in terms of number of nucleons, this is the value of ER. Now you see, the arguments for the stability of white dwarf can be repeated analogously to the case of neutron star. So that the critical condition for stability ER is equal to 0, it basically determines the maximum mass of white dwarf and results in the condition for the maximum mass, and also results in condition for maximum mass of nucleons. That means N max. Okay. So that this particular condition ER equal to 0 then gives us ultimately this relation. Fine. And from here you see we will get the maximum number of nucleons. So this is the maximum number of nucleons, right? Now it is important to note that here we have an additional factor compared to neutron star case. Otherwise you see the expression is the same as the degeneracy factors, right? Even the degeneracy factors are also the same for neutron star and white dwarf. As a result, the corresponding maximum mass, so maximum mass for the white dwarf, it is given by this value. Here, maximum mass of white dwarf. Okay. Now, again, if we compare this with the numerically exact one, then the Chandrasekhar mass in natural units can be written as, you see, over here. So, this is the exact numerical result, which gives us the Chandrasekhar mass. These two values. Now you see, except for the numerical prefactor here, which is of the order of 1, the expressions are the same. In fact, one recovers with Landau's argument the dependence of the maximum mass of white dwarf on the charge to mass ratio of the nuclei and the nucleon mass over here. Also note that the electron mass does not enter the expression for the maximum mass of the white dwarfs. And most strikingly, so let me write it down. Electron mass does not enter the maximum mass. This I have already discussed in one of my videos. Remember when I was talking about, since we are considering the ultra relativistic case. Now, most strikingly, you see these expressions for the maximum mass of neutron star and for the white dwarf are similar, and they just differ by the charge to mass squared ratio. So, if we want to summarize, then we can say that the mass of white dwarf is of the order of mass of neutron star, and this is mp cube by mn square. This is of the order of 1 solar mass. As the maximum mass in both cases is determined by the nucleon mass. Okay. Now the critical radius for the white dwarf, the critical radius again, it can be determined by considering the KFE equal to ME, right? And this will give us this value for the critical radius of the white dwarf. Now, again, we realize that the electron mass ME is entering one of our expressions here for the first time. It does, since ME does not enter the maximum mass, but it is entering RE over here. Now, using the expression for the maximum number of nucleons, we can further write this down as this, the critical radius expression. So, in terms of maximum mass, this critical radius is given by this, so that you see, so radius of white dwarf is how much? Of the order of, you see, mp by mp into me, right? And this is of the order of 5,000 kilometer, and this is again same as the size of Earth. Now note that the radius corresponding to the maximum mass of the white dwarf is related to electron mass, or more generally to the mass of the fermion that is providing the pressure. Now, the smaller the mass of this fermion, the larger the compact star. Now, if we compare this expression for the radius of white dwarf to that of the neutron star, we can see that they scale with the ratio of the proton to electron mass, which we have discussed, right? And so basically, the ratio of the white dwarf is larger by the ratio of the proton to electron mass. So you see, what I am saying is this. of the order of 1000. That is by 3 orders of magnitude. Now, indeed, this is what one finds in more refined models of neutron star and white dwarf, and also from observations. Now, you should remember that characteristically, the radius of a neutron star is around 10 kilometer, and again the radius for a white dwarf, characteristic numbers, is around 10,000 kilometers. Okay, so that's it for today.